Hey guys, so today we will understand how merge sort works. Merge sort. So guys, merge sort is one of the most classical sorting algorithms, and this is based on one of the most important paradigms of algorithm, and that paradigm is called as divide and conquer. Okay, divide and conquer. So first, let us understand what divide and conquer is. So basically, let's say if I have got a problem one, okay, whose size is say n. Okay, so divide and conquer strategy is that you divide this problem into smaller problems. Okay, in the problem into the problems of smaller size. So let's say I divided it into a problem of size n by 2 and another problem of size n by 2. Now, once let's say this subproblem somehow magically gets solved. Once this gets solved, I receive its solution, that is solution 1. Okay, this also somehow gets solved, so I receive its solution, that is solution 2. Once I have got solution 1 and solution 2, that means the divide part of divide and conquer is over. Okay, so now I can conquer these solutions and formulate the final solution. So that final part which leverages solution 1 of subproblem 1 and solution 2 of subproblem 2 and does something on top of it to get the final answer is called as conquer. Okay, so this is the very high level explanation of divide and conquer paradigm. Now let's try to correlate this divide and conquer paradigm with our merge sort, that how our merge sort leverages it. So let's say I have got an array of size n. So what I would do is I would break this array of size n into two subarrays of size n by 2. Okay, these are two subarrays of size n by 2, and let's say somehow this particular subarray gets sorted magically. Okay, so I receive the sorted version of this. Okay, now this also gets sorted magically. I receive the sorted version of this. So now finally I need to conquer the two sorted portions. This is sorted 1, this is sorted 2. So now somehow I need to conquer these two sorted portions such that I get the eventually sorted array of the larger problem. Okay, so how do I do that? This conquer thing with respect to merge sort is called as merge procedure. Okay, so what merge procedure does is it receives two sorted arrays and it merges them into final sorted array. Okay, so let us try to understand how merge procedure would actually operate. So if I have an array that contains 8, 7, 6, 5, 4, 3, 2, 1. Now let's say I divide it into two parts, 8, 7, 6 and 5, and the other part containing 4, 3, 2, 1. By the time this problem is solved, this portion has become, 5, 6, 7, 8, and this portion has become, by the time this has been solved, 1, 2, 3, 4. Now I need to perform a merge action. I need to perform a merge action so that this gets converted into 1, 2, 3, 4, 5, 6, 7, 8. So how do I do that? So let's learn about merge procedure. It takes in two sorted arrays. First sorted array is 5, 6, 7, 8, and the second sorted array is 1, 2, 3, 4. It takes two pointers I and j. Okay, both of them are initially pointing to the first element of both the subarrays, and it takes an auxiliary array of size equal to size 1 plus size 2, where size 1 is the size of this and size 2 is the size of this. So since there are 8 elements, I need 1, 2, 3, 4, 5, 6, 7. Okay, so these I and j pointers are positioned in a way that either of them qualifies to be the current element. So whichever is smaller qualifies to be the current element. So since this is the smaller, 1 comes here and I move this pointer. 2 is smaller than this, 2 comes here, I move this pointer. 3 is smaller than this, 3 comes here, I move this pointer. 4 is smaller than this, 4 comes here, I move this pointer. Now this array is over. The moment one of the sorted arrays is over and some elements are remaining in the other, that means all the remnants of that array are greater than all the elements that have been inserted till now. And since this is sorted in itself, it can be pushed as it is in this particular auxiliary array. So it's just a matter of putting them one by one over here. Okay, so I will do 5, 6, 7. So this is what the merge procedure is. The time complexity of this is order m plus n, where m is the size of first sorted array and n is the size of second sorted array, because you can see that every element is getting touched only once. Okay, every element is getting touched and pushed only once. So that is the reason. Now, in context of merge sort, let's try to understand how this merge procedure actually operates. So I will take an array, let's say that contains 8, 7, 6, 5, 4, 3, 2 and 1. So first what I do, I divide it into 8, 7, 6, 5 and 4, 3, 2, 1. I will merge once this problem and this problem has been solved. So first this problem will be solved, right? According to recursion, first this branch has to be solved, then only this would proceed. Now to solve this, again I break it into 8, 7 and 6, 5. And then I perform merge. Merge would be performed when this is sorted and this is also sorted. Now for this it gets broken into 8, into 7, and then merge would be triggered. Okay. Now see, the moment the two sub-arrays are of size 1 each, no further breaking down can happen. So this is the termination condition. The moment I have reached termination condition, what is termination condition? When both the sub-arrays are of size 1 each. So no further calls happen, merge happens. So merge happens, what would happen? That I take an auxiliary array of size 2, and as I described, I would get a sorted array 7, 8 in that auxiliary array, and then from that auxiliary array I can copy that contents back to here. So if I got a merged auxiliary array like this, I copy this back in the original input. So now this has become 7, 8. So basically this problem has been solved. Similarly, same thing happens here. This gets broken to 6, to 5, and then merge kicks in. The moment merge kicks in, it merges them into an auxiliary array and copies the content back over here. So I get 5, I get 6. Now this merge would kick in, because for this problem, the half of this has been solved and half of this has been solved. So the next thing is merge. So it merged this and this in an auxiliary array, and it would give me 5, 6, 7, 8, which would be copied here, and it would become 5, 6, 7, 8. Same thing that happened for this part would also happen for this part, and this would get converted to something like 1, 2, 3, 4. Once this is sorted, so the merge of this entire thing would happen, and there would be an auxiliary array that would contain 1, 2, 3, 4, 5, 6, 7, 8. This entire thing would be copied here, and I would get the eventually sorted array as 1, 2, 3, 4, 5, 6, 7, and 8. So this is how merge sort operates. So if I have to write the pseudo code for merge sort, it is simple. Merge sort would take in an array, its start index and end index. Okay. As I told you, the termination condition is size 1. So I would make further calls only when the size is not 1. It is greater than 1. So if I is not equal to j, it indicates that there are more than one element. So in that case, first thing I do is I find the mid, which is I plus j upon 2, and then first I call the merge sort for the left portion, which is from I to m. Then I call the merge sort for right portion, which is from m plus 1 to j. Once this portion is sorted and this portion is sorted, I call merge of this sorted portion and this sorted portion, m plus 1 to j. So this is the pseudo code for merge sort. Merge procedure you can easily write on your own, where Merge procedure would take in starting and ending of one sorted array, sorted subarray, and starting and ending of second sorted subarray, and merges them accordingly. So now let's discuss about the time complexity. So you can see that at every level, the size is getting halved. So how many levels will be there? In the last level, there is only one element. And since this is becoming n to n by 2, n by 4, n by 8 and so on, number of levels would be log of n base 2. And now, in each level, how many operations are happening? So in each level, in the last level, okay, in the last level, there are n elements of size 1 each. Okay. In the second last level, there are n by 2 elements of size 2 each. In the third last level, there are n by 4 elements of size 4 each. So I can say that at each level, number of elements are n into 1, that is n, n by 2 into 2, that is n, n by 4 into 4, that is n. So how many merges would happen? Number of merges would be equal to the number of elements. So in each level, order n merge operations are happening, and since there are log n such levels, so overall time complexity would be order n log n. Let's also discuss about the space complexity. So since I told you I need an auxiliary array to temporarily merge and store the contents, okay, so what would be the size of that auxiliary array? That would be aux of size n, because at max there would be two subarrays of size n by 2, n by 2 each. To merge them, I need an auxiliary array of size n. So that's it. That's about the time complexity and the space complexity. I hope you understood it. That's it. Thank you.
Merge sort is, if imagine you had to sort a deck of cards. One possible way, which is, by the way, also called divide and conquer, could be that I break down this deck of card to half deck of card and half deck of card. So I divide into two parts, right? Like half goes, let's say, to the left, half goes to the right. I sort those individually, right? So half deck of cards, I sort them somehow by some magic. And right side also I sort somehow by some magic. So now I have two sorted deck of cards, right? I have two sorted deck of cards. Now the problem becomes, if I have two sorted deck of cards, can I merge them so that they still remain sorted? Imagine, let me give you an example, right? So let's say I have an array 2, 3, 5. Let's say I have another array 1, 6, 8. If I was given these two arrays, can I merge them into another array which is completely sorted? Is that possible or not? If that is possible, then this could become another algorithm, which is like whenever I need to sort an array, I can divide it into two parts, recursively sort them, and then I can merge them. So merge becomes the important step. The question is, I have given you a problem. You have two arrays, not necessarily of the same length. Let's say this is of size A, this is of size B. Can you create another array of size A plus B where all of the elements come from A or B and they're all sorted? Is the question clear? Like you have some A number of arrays in array A, you have B number of elements in array B. Array A and B are individually sorted. So A is a sorted array, B is also a sorted array. You have to merge them into another sorted array. How would you do that? Basically, if I have been given two numbers, let's say I have an array A, 2, 3, 5, and I have an array B, which is, let's say, 1, 4, 8. And I have to create a sorted array, right? Which is of size 3 plus 3, which is 6. 1, 2, 3, 4, 5, 6, correct? This is the eventual sorted array I have to contain or create. One thing is, the first element in the sorted array is going to be the completely minimum of everything in the array, right? So given array A is sorted, minimum from array A is on position number 0, correct? Minimum from array B is also on position number 0. So therefore, whichever is the minimum of these two, I don't need to look at any other element. Whichever is the minimum of these two is going to be the first element in the sorted array. Is that something you all agree with? And what is the minimum of these two? Minimum of these two is 1. So 1 comes here. Now, if I have inserted 1 here, then it is as good as saying that now I remove 1 from B. It is the same thing, right? So what I just do is, how do I remove 1 from B? I just change this pointer to now point at this number 4. This is as good as saying that I'm now merging two arrays, one array which is A and one array which is B, but B is starting from this point onwards. And I again do the same thing. what is the next number that should come here? It should be the minimum of numbers here and minimum of numbers here. What is the minimum of numbers here? Array at this pointer. What is the minimum of numbers here? The array at this pointer. Whichever is smaller, which is 2, comes here, and this pointer moves one step forward. So in short, the approach becomes that you have 2 pointers. Let's say there's a pointer 1, which is for array A. There's a pointer 2, which is for array B. And you just say the following: while pointer 1 is less than whatever is the size of A, and pointer 2 is less than size of B, you do the following. You figure out which one is smaller. You just check. If A of pointer 1 is smaller than equal to B of pointer 2, then simple. This is what goes in the sorted array. So let's say sorted of, let's keep an index, A of pointer 1. You increment the pointer 1 plus plus because now pointer 1 has been assigned here. Else you put pointer 2 element here. So sorted of, again, index plus plus is equal to B, pointer 2 plus plus. The only thing is, when I'm done with this while loop, it is possible that all of the smaller elements were in one of the array. Imagine like this array was 1, 2, 3 here, and there were, let's say, 4, 5, 6 here. My pointer 1 will end up going here, and I'll end up breaking out where I've only filled in 1, 2, 3 in the sorted array. 4, 5, 6 is yet to be filled. So I'll have to check for that, which is at the end of this while loop. If whichever pointer is not done, so I just check while pointer 1 is less than size A, I just keep adding sorted of index plus plus is equal to A of pointer 1 plus plus. And very similarly, I do the same thing with pointer 2. While pointer 2 is less than size of B, same thing, sorted B of pointer 2 plus plus. Right. That will cause the merge to happen. Does this make sense? Right. Now, if that can happen, which means now if merging can happen, and what is the time complexity of this merge? Imagine I have 2 arrays of size n and n each. M plus n, right? Like, so it takes me order n time to merge. If in fact the array A was of size m, this was of size n, it takes me order of m plus n time, right? That means if I have a order n array to be sorted, if I divide it into 2 parts, I say that sort the first part separately, sort the second part separately. Once they are sorted, then merging them will take me order of n by 2 plus n by 2 time, which is order n time. So merging them will take me order n time. Now, how do I sort the first half of the array? I can do the same thing with the first half as well. I can say that even to sort the first half, again break it down into 2 parts, and then sort the first half, sort the second half, merge it. With the end condition being that once I have an array of only size 1, it is already sorted. How about I modify this and I say that I have 3 arrays that need to be merged, right? Imagine I have an array 2, 5, 10. Imagine there's another array 1, 8, 9. And imagine there's another array 3, 4, 12. Let's say there were 3 arrays, right? How would you merge these 3 arrays into one array, which has all elements are sorted? We can do 2 at a time, but we don't necessarily need to, right? Like, we look at this, right? What is the first element going to be in the merged array? It is the smallest of all. Where does the smallest come from? It is either the first element from here, or the first element from here, or the first element from here. Whichever is the minimum from here, that becomes your smallest. So I can have 3 pointers. Pointer 1 pointing to the 0th element, pointer 2 here, pointer 3 here. Whichever is the smallest of these 3, which in this case is 1 comes here. And then all I do is I move this pointer 1 step to the right. And I again repeat the same thing. Whichever is the smallest of these 3, which is 2 comes here. And then 2's pointer moves 1 step to the right. Now again, 5, 8, 3, whichever is the smallest, 3 is the smallest, 3 comes here. And 3's pointer moves to the right. 5, 8, 4, 4 is the smallest, so 4 comes here. And its pointer moves to the right. 5, 8, 12. 5 is the smallest, so 5 comes here. And 5's pointer moves to the right. And then so forth, right? In the case of merge sort, it is only 2 arrays. An extension of the previous question. Then instead of 2, if there were 3 arrays, how do you go about merging 3 arrays? I mean, you can merge 2 arrays at a time. You can merge these 2 at a time, and then you end up merging these 2. but you'll end up using more memory, because to merge these two, you'll need an additional array of size 6. Then you'll create an array of size 9. What I'm doing is I'm just directly creating an array of size 9 so that I reduce the amount of memory required to maintain that intermediate re-array. Also, I reduce a step. Okay, all right. Coming back to the merge sort. How does merge sort work? As the name suggests, it's divide and conquer, which is basically, now that I know that I have the superpower of taking two sorted arrays and merging them, what I can do is, given an array A, I sort the first half. So sort A to 0 to n by 2, sort A of n by 2 plus 1 to n, and then merge these guys. That can become my approach. And this, how do you sort the first half? This also can happen in the same way, where you again divide into two parts, 0 to n by 4, and then n by 4 to n by 2, and again, then you merge, etc., right? And if I have to write code for this, it becomes fairly simple, which is, let's say if the question was, how do you sort array A from index I to index j? If obviously like the size of the array is already 1, which means if j is equal to I, let's just put that, then your array is already sorted, so you can just directly return. If not, then what you do is you basically sort the first half, which is you say, I'll go from A of I to mid, where my mid is I plus j by 2. Then I'll sort A from mid plus 1 to j. And once these two guys are sorted, then I will need a temp array where I'll merge the array from I to mid and mid plus 1 to j. And then I'll make sure that A of I to j becomes equal to temp. I'll just do that. But basically, I'm just applying recursion here. And what I'm saying is, if you want me to solve, by the way, let's say there are 4 numbers, right? 5, 3, 2, 6. Let's say those were the 4 numbers. I say that first sort the first half. So let me call the function to solve these 2 numbers, 5 and 3. Somebody sort this and then give it to me. And then sort the second half separately. So somebody sort 2 and 6 and give it to me. And once I have them sorted, then I will actually merge them, right? Now to sort 5 and 3, I again do the same thing. I split it half. I say somebody sort 5 for me and somebody sort 3 for me. Here also somebody sort 2 for me and then 6 for me. Once they are sorted, then I'll merge. 5 is sorted, 3 is sorted. How do I merge? In my merge step, the same way we had seen, we have 2 arrays. We have to merge. When we merge, this will become 3, 5. And that is what I replace my original array with. So this array becomes 3 and 5. Very similarly, 2, 6 remains 2, 6. And then once I have 3, 5 and 2, 6, then I merge them to find 2 comes first, then comes 3, then comes 5, then comes 6. And this becomes my actual sorted array, which I replace this with. Just out of curiosity, why do we divide them into equal halves? Although in the end, we move 2 single elements and merge them in sorted order. Can't we take pairs in the array and do the same way of merging? Let's say I have more numbers, right? So imagine I had 5, 6, 8, 1, 2, 13, 15, 12, 3. How many do we have? We have 4. And let's imagine I remove 12 from here. Question is, if we have to sort anyway, why don't we take pairs by pairs, right? So let's just take pair 5, 6, 8, 1, 2, 13, 15, 3. And let's just first sort them. So we end up sorting them. And for example, we end up finding that this is 5, 6. This becomes 1, 8. This is 213 and this becomes 315, right? Now the problem is like we've done pairwise sorting, but the array is still not sorted. Then we'll have to do sorting of 4 elements each, right? How do we do that? We say that, you know what, like there are first 4 elements here. The first half is sorted. The second half is also sorted. Let's merge somehow, which again, I'll take another array and then I'll merge, etc. So this will get sorted. Then I'll do again the same thing, which is I take 4 elements, half is sorted, and I'll do the same thing. And then finally, I'll look at all of the 8 elements. So you're going just in the reverse order. What I just said, you're just going in the reverse order, which is also correct. It's just harder to code because the previous approach can be coded using recursion, which I'll just show. In your approach, what you're doing is you're building bottom up, right? Like you're sort of saying that let's first sort all pair of elements. Once they are sorted, then let's look at all 4 size elements. Great. Once they are done, then let's look at all 8 size chunks. Once they are done, then look at all 16 size chunks, and then 32 size, and then 64, and so forth. Right? And finally, I'll have the entire array sorted, which works. It's just harder to code. What I said was the other way around, that instead of going from 1 to 2 to 4 to 8 and so forth, let's start from n. Let's divide that into n by 2 parts, then n by 4, then n by 8, and I'll finally reach the 1 part anyway. And then my recursion function will keep returning, and I'll have the eventual answer. So if you look here, my recursive function, this will do the same thing. My recursive function here will also do the same thing. Let me also just write it as merge step. So what is happening is, if I have an n-sized array, I'm dividing it into 2 arrays of size n by 2 each, n by 2 each. I'm sorting it using the same methodology, which is this n by 2 will create arrays of size n by 4, n by 4. Here also, again, same, n by 4, n by 4. These will create arrays of size n by 8, n by 8, again, n by 8, n by 8, same thing. And this n by 16, n by 16, and so forth. How many levels will you have here? I mean, we go from n to n by 2, n by 2 to n by 4, n by 8, 4 to n by 8, n by 8 to n by 16. How many levels? Log n levels, right? So in every level, n is becoming half of what it was. As we have seen the same pattern in binary search, etc., etc. I mean, as you go, if n is becoming half of what it was, it takes you log n steps to finally come to 1. At every step, what is happening? At every step, basically, I have n by 2 sorted array. I'm merging them, which takes me order n time. This takes me order n time. N by 2 plus n by 2 and order n. What happens on this level? These 2 guys merge and it takes them n by 4 plus n by 4, which is n by 2 time. These 2 guys merge and it takes them n by 2 times. If you add them up, it will take you order n time on this level as well. Very similarly, on the other level as well, where you have n by 8, there are 8 instances of n by 8. It will again take you order n time. So the total time taken on every level, it takes you order n time. There are log n levels. The total time taken is n log n. That is an intuitive way to understand. I can also explain the mathematical way of explaining this. But the intuitive way of understanding the time complexity of merge sort is that on every level, you're doing one merge. The merge is order n. Number of levels is log n. And therefore, in fact, if you look at Arvind's approach, if you were to implement it, in every iteration, what you're doing is you're first creating pairs and you're merging the pairs. Takes you order n time. Then you're looking at all 4 blocks, right? Like blocks of 4 each. In one order n operation, you will have sorted blocks of 4 each. Then in again one order n operation, you would have sorted blocks of 8 each. And you'll keep doing that till you cover the entire array. So the number of steps to cover the entire array would be log n. And every single iteration is an order n iteration. So it takes you an order of n log n. I can explain the math behind it as well. Is it n log n in every case? Best case is, sure, I mean, you can probably put an optimization there that if the array is already sorted, if a half is already sorted, you don't need to do all of the splitting, etc. So best case, you can still make order n. But yes, worst case is order n log n. Worst case, it takes you order n log n. And you can put a check to make sure that you're not doing the entire splitting, etc. if the array is already sorted. All right. What is the space complexity of merge sort? So if you look at the implementation here, we are allocating this additional memory temp to calculate this merged part, right? Why? Because when we are merging two sorted arrays, we need this temporary space where we put in the result, which is not a part of the original array. This is additional space. If I have to look at this tree, in this n by 2 part, I would have taken a temp array, which was of size n by 2. Here, I would have taken a temp array, which was of size n by 2. In fact, let's look at total space allocation, right? So this n by 2 will make a call to n by 4, 8, etc., etc. So this is a log n stack memory space. Plus, in each of these, so imagine I was sorting this array of size n. This will end up calling for n by 2. This will end up calling for n by 4, n by 8, and so forth. In each of this, I would have a temp array allocated, which will be freed as long as, I fill it back, right? So this temp array here is of size n by 4. As soon as I am done, then this will be freed. Then I come back here. Here it will be of size, additional size of n by 2. As soon as I'm done, it will be freed. And then I'll come back here and I'll have a temp array additional size n. So maximum space that I end up using additional is I have log n stack of recursion, plus I have this additional order n size array that I might have used, which is my temp array. So order n extra space is what we end up using apart from the array space. So space complexity becomes order n. Time complexity becomes order of n log n. There's one more way to, by the way, calculate time complexity. I mean, if you assume that the time taken for sorting an array of size n is tn, then tn is nothing but, I'm saying, first sort array, first half of the array, then sort second half of the array, which is also of size n by 2, and then merge them, which is it takes you some n time. Let's say it takes you n time. This is basically saying 2 times t n by 2 plus n, right? If you break it down further, your n by 2 is 2 times t n by 4 plus n by 2, which is the same as 4 times t n by 4 plus 2n, which you'll see will finally come to 2 to the power I t times n by 2 to the power I plus n into I. I mean, this is just a little mathematical. Therefore, I explain the intuitive way first. Which, I mean, if you want this to become equal to 1, I becomes log n. So you have n into t times 1 plus n into log n, which is n log n. This is how Master's theorem actually works. I'm just elaborating that, expanding that equation. Even if you don't know about Master's theorem, that is fine, as long as you understand the intuition of why it is n log n. Because in the recursion tree, there are log n levels. On every level, I'm using order n time. So time complexity becomes order of n log n. Space complexity becomes order of n. Is there any way without using the extra space? So actually merging two sorted arrays without using extra space in order n is not possible. That becomes the blocker, right? So if you can merge the array in place without using extra memory, then your problem would have been sorted. But the problem is like merging without extra memory is the issue. All right, does this make sense? Merge, sort, space complexity, time complexity, all of that. All right.
If you like the video, please do not forget to like, comment and share this video with all your friends. Also, subscribe to our channel to get notified about the new upcoming videos.